Okay, Wilhelm, are you ready?
I'm ready.
All right, very good. So good day, everybody. It's a pleasure to have Wilhelm Winter from the University of Münster today as our speaker. And he is going to tell us about completely positive approximation revisited. Wilhelm, please.
Thank you very much. Thanks for showing up. Thanks for the invite. It's great to speak in the NCG seminar. Seems I'm a week late. My talk was supposed to be on the 12th, but then Wilsby kindly agreed to reschedule. So this is going to be about completely positive approximations and some new aspects of those. And it's joint work in progress with Christian Courtney. Christian has spoken a few weeks ago about this already in the European node of the NCG seminar. And so apologies if a few things are a bit repetitive, but I'll try to emphasize a few other things, and one or two things have also happened since then. So we'll see how it goes. Recall that, I mean, we start with the C-star algebra A, and then we say, I want to define what a system of completely positive approximations is, and that's a net of diagrams like this, where you have maps from A to F lambda and back to A, such that the F lambda are finite dimensional C-star algebras, and the phi lambda and the psi lambda, and I refer to psi lambda as downwards map, which isn't so visible right now, but it'll become clear later on, and to the phi lambda as upwards maps, such that these are completely positive maps with a uniform norm bound. And often one assumes that they're completely positive contractive, but for some reason, which will also become clear later, I want to insist only on a uniform norm bound, but that's good enough. It's equivalent. Okay, and then by system, I mean that these converge to the identity map in point norm topology. Right, and nuclear C-star algebras are precisely those admitting such systems, and I'm using this as definition of nuclearity. The completely positive approximation property. Nuclearity, of course, is the C-star algebra analog of amenability, and there are as many characterizations of nuclearity for C-star algebras as there are for amenability of groups. Maybe not quite as many, but and nuclear C-star algebras, they form a very robust class of C-star algebras. And to illustrate that, let me recall some much older sample results. So here's a combination of results from Bunce, Christensen, and PC. Says nuclear C-star algebras are precisely those with similarity degree 2. I don't want to define what this is, but in particular, they satisfy Cadison's similarity property. And that means that every bounded representation is similar by conjugation with some operator, some invertible operator, is similar to a star representation. Okay, that's one slightly surprising feature of nuclear C-star algebras. And here's another theorem which says that nuclear C-star algebras are stable under small perturbation. So in other words, they satisfy the Kelsen-Kastler conjecture. And this means if we have two nuclear C-star algebras, and in fact, we only need to know that one of them is nuclear, which act on the same Hilbert space. And suppose, yeah, there's a typo. If we have two C-star algebras which act on the same Hilbert space, and so my tablet kicks me out as soon as I make a mistake, as soon as there's a typo. So if we have two C-star algebras acting on the same Hilbert space, and one of them is, say, separable and nuclear, and suppose their unit balls are within a small number of each other, 1 over 420,000 is enough, small enough, then these two C-star algebras are isomorphic. So it's you can always shake them a little bit and they stay the same. Here's another theorem combination of several results by a whole bunch of people, myself, Matsui Sato, and this 5-author team. Suppose A is a C-star algebra. Suppose it is separable, simple, unital, and nuclear, and it's not finite dimensional. It's not matrices. And then the following properties are equivalent. First, A has finite nuclear dimension, and second, A is isomorphic to A tensor Z. And I will define nuclear dimension in a moment. Bear with me. I will not define the Jiangsu algebra Z. You can think of this.
Yeah.
Question.
Can you say just a few words about this Z? I mean, you know, yeah.
Yes. So very few words is it's the smallest possible C-star version of the hyperfinite to one factor. That's one way of describing it in a meta way. Okay. I mean, the very smallest version is the complex numbers, but that doesn't deserve mentioning. So it's an infinite version of the complex numbers. You can think of this as, think of the K algebra M to infinity, and then compare this with M3 infinity. So take these two UHF algebras, and these have non-trivial K theory, of course. And this algebra Z, you can think of as a bundle with on the interval with values in M2 infinity tensor M3 infinity, with boundary condition that on one side it's M2 infinity, on the other side it's M3 infinity. So K theory vanishes, and then use C-star algebra trickery to make this bundle a simple C-star algebra.
Okay, good. That's very good. Okay.
That's one way to describe. There are other characterizations, and so it's a version of a UHF algebra without matrices, and the property of being Z stable, A is isomorphic to A tensor Z. I mean, this is the minimal C-star algebra tensor product here. The property of being Z stable is the right C-star version of being McDuff.
Okay, very good.
Okay, and then this theorem is the C-star algebra analog. I think it deserves this this name. It's a C-star algebra analog of the fact that for Neumann factors, for injective factors, you have hyperfinite is equivalent to McDuff. And in phenomenal algebras, this is simply a fact. It's a theorem. But both of these simply hold for injective factors, but for C-star algebras, they do not hold automatically, but they are equivalent. And this equivalence, this was of course part of the proof that in phenomenal algebras, in Alain's theorem. Okay. So, and then we also get a C-star algebra version of the classification theorem. So this is really by many people. Look at the following class of C-star algebras, this class here. It's the class where A is separable, simple, universal, and nuclear, and it satisfies the universal coefficient theorem. If you don't know what this is, think of this as a notion of weak homotopy equivalence to a commutative C-star algebra. And it's an open, it's a hard, important open question whether all nuclear C-star algebras satisfy the UCT. But let's disregard this for a moment. And then if you take these C-star algebras, and then you notice they may or may not be Z stable. But if you force them to be Z stable, if you tensor on the Jiangsu algebra, then this class is classified by the Elliott invariant, namely essentially K theory plus traces, and the pairing of traces with K theory. Okay. And for all of these results, one really has to understand completely positive approximations. That's the key. So let's look at these in a bit more detail now, and add some extra structure. So here's the definition of nuclear dimension that I promised you. Again, A is a C-star algebra, and then we say A has nuclear dimension at most D. If the following holds, there's a system of CP approximations as before. So A maps to F lambda, maps back to A, such that the downwards maps psi lambda are contractions. They're completely positive contractions. And for each index lambda, we can decompose the C-star algebra F lambda into a sum of D+1 finite dimensional C-star algebras. These F lambda super I, they're not matrix blocks, they're finite dimensional C-star algebras, potentially very big ones. And then you say that we want that for each of these indices, of these super indices, for each K, the map phi lambda, when restricted to this summand, is again contractive. It's completely positive contractive, and it has order 0. And by this, and this means that it preserves orthogonality. So if you have two elements in one of these summands, which multiply to 0, then their images under phi lambda also multiply to 0. Okay, and for star homomorphism, this is of course true. But order 0 maps, they're in between general completely positive maps and star homomorphisms. But they're genuinely more flexible. Okay, and it's supposed to be a system. So again, it's supposed to approximate the identity map in point norm topology. And in this situation, if A has finite nuclear dimension, one can in addition arrange that the psi lambda are approximately order 0. And this means if we have two elements A and B in the C-star algebra A with 0 product, then psi lambda of A times psi lambda of B also converges to 0. Okay, the norm of this product. And if notice that in this definition, the phi lambda, they're phi lambda restricted to each of these summands, they're contractive. Okay, and there are sums of D+1 contractive maps, the phi lambda. So the norm of phi lambda is at most D+1. So there's a uniform norm bound. If we can reach in addition that the phi lambda are contractive themselves, the sum of these order 0 things is contractive, then this is a different concept. And then we say A has decomposition rank at most D. This is what I did a long time ago with Eberhard. All right, and in this case, if we have decomposition rank small d, then one can arrange, in addition, that the psi lambda are approximately multiplicative. So then we don't have just this approximately order 0 condition. We have that approximately the psi lambda pick up the multiplicative structure on the nodes. All right. And it turns out that in this setup, the crucial information is encoded in the maps phi lambda. The maps psi lambda are not so important. Let me show you a one-sided version of this. And this appears in work of Sato for decomposition rank, but I'm going to show you a version that also works for nuclear dimension. And in the paper of Sato, it's phrased a bit different, but it's really it's not hard to get from his version to the version I'm going to show you. So it goes as follows. Let's assume, to avoid technicalities, that C star is universal, and then the nuclear dimension of A is small d if and only if the following holds. Whenever you have a finite subset curly F, say this contains the unit, and it's finite subset of the unit ball of the positive elements of A, we have some tolerance epsilon, then there's a map phi from F to A, so there's a finite dimension C star algebra in the map phi such that F is finite dimension, as I said, and can again be decomposed into d+1 summons, and such that phi k, when restricted to each of these summons, is completely positive contractive and has order 0, preserves orthogonality as before. And whenever we have an element in this finite subset here, then there's some element B sub A, just some element, which in the unit ball of the positive elements of F. And then, of course, this also has this decomposition into the various summons of F, such that this element is almost sent to A. That's one condition. And in addition, when we take A, our element in curly F, when we take A and we multiply it with phi k of this element which belongs to the unit, or which almost goes to the unit. If we multiply this, then this way we can almost excise the element phi super k of BA of the kth summit. Okay, so we can this way we can excise by compression with the image of the unit of the kth summit. We can almost excise the map phi k.
I'm confused by the notation. I mean, when you say B sub 1A K, you mean the unit in the block in the block K?
Yes. No. I mean the element B which belongs to the unit. I assume that the unit of A is in this curly F.
I understand, but then it seems you repeat B twice. I mean, or what? Because I mean,
I repeat. Because I mean this it's slightly funny notation. I agree. This B sub A, this is just some element which is close when I send it when I apply phi, which gets close to A, and when I take little a as the unit, which I'm allowed because the unit of A is contained in F. Right? When I take little a as a unit, then I also have some element B.
I understand. Okay, so it's really confusing notation. Yes. Okay. Fine.
I know. It's a bit technical and a bit confusing.
Yeah, but I mean, what it means really, it is something which is related to the unit in the local block. Yeah, the file. Yeah.
For nuclear dimension, it could be far away from the unit. It's just the image of the unit.
Yeah, okay, sure.
For
Okay.
decomposition rank. So
Yeah.
if it's the unit, and if B sub 1 is the unit in the local block, then this characterizes decomposition rank.
Okay, good.
But in general, this B sub 1, this is just a positive element which in norm could be far away from the unit of the matrix algebra.
I understand. Okay.
And we'll come back to this. And the point is that with this condition here, which doesn't show up explicitly in Sato's version of the this one-sided characterization, with this condition, it's very easy to find these local inverses psi. And this is a subtle difference. It's a subtle point, and I'll come back to this. So this is actually fairly easy to prove. Just as a remark in between nuclear dimension and decomposition rank, they capture at the same time algebraic and topological information. Let me give you one example. If A has finite nuclear dimension, then A is commutative if and only if in these approximations I gave you, the F lambda are commutative. So this is something you can read off straight away from these approximations. For topological information, the nuclear dimension of continuous functions on a, say, Hausdorff space X is just compact Hausdorff space X is just the covering dimension of that Hausdorff space.
I mean, the Lebesgue dimension, yes, yeah. Lebesgue
in the second countable case, they're all the same, and in general you have to use the right version of covering dimension, and in this case it's Lebesgue dimension. Yes. But in this, if X is second countable, then if it's metrizable, then they're all the same, all these covering dimensions. And then one can ask, if we don't have finite nuclear dimension, which one doesn't always have, just assuming nuclearity, are there still approximations in a similar style? And the answer is yes. So here's a result by Hirschberg, and White, and later refined by Brown, Carrion, and White, which goes as follows. When you start with a nuclear C-star algebra A, then this has a system, as before, of completely positive approximations, such that the phi lambda are now convex combinations of contractive order zero maps. And the psi lambda are all contractive and approximately order zero in this sense I explained before. So the way this works is one has to go through the proof of Choi-Efros of the completely positive approximation property for nuclear C-star algebras very carefully and pick up these additional properties. So this is not an easy statement if you don't have this proof at hand already. And moreover, if A and all its tracial states are quasi-diagonal, then one can, in addition, arrange that the psi lambda are approximately multiplicative, not just approximately order zero, but in fact approximately multiplicative. And recall that quasi-diagonal for C-star algebra means there's sufficiently many approximate representations on finite dimensional Hilbert spaces, and approximate representations, I don't want to make this precise, and for the tracial states to be quasi-diagonal, this means that the tracial states on the C-star algebras are picked up by these approximate representations followed by the canonical tracial states on the matrix blocks. Okay, and every trace can be expressed in this way. And just as a comment in between, even when you take continuous functions on the interval, say, then writing down approximations like this explicitly is not entirely straightforward. It's not the first thing that comes to your mind. And it's a nice exercise to do this. And the point is that we want convex combinations of contractive order zero maps. This is one has to fiddle around a little bit. But I don't want to describe these explicitly right now. Here's another problem related to this, and which refers to the one-sided version of nuclear dimension that I described. Question: is there a characterization of nuclearity which, along these lines, which avoids the maps psi lambda? And if it's one that I have in mind, then this would yield a direct proof that the completely positive approximation property passes to quotients. And from this, you can already guess that if there are such characterizations, they're not going to be, it's not going to be easy, because this statement that CPAP passes to quotients, it's a hard statement. And I'll come back to this problem a little later. Now, for a moment, let us assume A is separable, and let's restrict to systems of approximations where the index is just the natural numbers. Okay, this is not so important. It's just a red herring, but for some of the statements to be true, as I put them, I need this. And then what I want to do is the following. I start with, let me write this here. I start with A, and then I take the downward map to F0 and upwards back to A. Fine. And then I repeat. I take the next approximation step, and now I go to F1 and back to A, and I do this F2 and back to A, and I keep going. Okay, and then for this to give me sufficient information about A, it's pretty clear that I have to be careful about the next approximation step. I have to in the next step I have to approximate not only the finitely many elements that someone gives me, but I also have to approximate the image of F0 when I take the approximation F1 and so on. So I have errors which keep accumulating, and I have to choose approximations in the next step such that these errors are summable. Okay, but if I do this, then I'm entitled to hope that if I only take the lower row with maps being just the compositions, I'm entitled to hope that the lower row will encode the C-star algebra A. It should contain all the information about A. Okay, if I'm careful enough about summing up errors and so on. And now the situation has shifted a little bit, because now I have just systems of finite dimensional C-star algebras with completely positive maps between them. And now the question is, when does such a system really describe a C-star algebra, and also how to read off information about the C-star algebra from this system? Okay, I have these maps between finite dimensional C-star algebras, and then I can form a limit in whatever category. And then the question is what does X have to do with the C star algebra? And if the lower row arose in this way that I just described, then X better be isomorphic to A in some sense, of course. But I would also like to know whether I can just look at the system and determine whether it comes from a C star algebra. So it's like a game. You give me a system of finite dimensional C star algebras with CP maps between them, and I look at the system and determine whether this actually came from a C star algebra or whether it's just something you made up. You could just give me some noise which has nothing to do with the C star algebra. It could just be random maps. Okay, so these are the questions I'm asking. So first of all, you might want to know what structure does this inductive limit have in the first place? Can we characterize when the system comes from a C star algebra, or at least when the limit is isomorphic to C star algebra in a reasonable way? And under which conditions are there abstract conditions on the system which allow us to recover the C star algebra A? Okay, and then once this works, then we would also like to know how to read off information on A from the system itself without having to recover the C star algebra explicitly. Maybe it's very hard to recover the C star algebra, but it might be much easier to extract certain information, like as an example, the commutativity of A, which we could read off very easily from the system straight away without having to determine the spectrum of the C star algebra. Okay, and of course, the kind of information I have in mind is K-theory and traces. So here's the definition, a concept that was introduced a while ago by Blackett and Kirchberg, and Christian and I generalized this a little bit, and it's goes as follows. Look at an inductive system like this, where the Fk of finite dimensional C star algebras and the connecting maps are completely positive contractions. Okay, and then Blackett and Kirchberg, they defined this to be asymptotically multiplicative if the following holds. And now it's a little bit technical, unfortunately, but it doesn't get easier than this, but it also doesn't get harder. There's no way out. It's nobody's fault. Whenever we fix some index capital K and X and Y in Fk at this stage, at this index, and we fix some tolerance, then there is some bigger index, capital M, bigger than K, such that whenever we have two indices, little m and little n, bigger than this bigger index, then rho mn on Fm and on these images of X and Y in Fm is almost multiplicative. That's what this says. So rho mn picks up the multiplicative structure approximately on the images of X and Y at a later stage. So the system is not multiplicative right away, but if you have two elements here and you move them along your system, then at some point the maps will start to pick up the products. They will start to be multiplicative, at least on these elements. Okay, and here I think it's not about confusing notation. It's just what one has to do. It's like definition of Cauchy sequences. It's a little. It's one extra step, and one just has to make this. Okay, this is asymptotically multiplicative. And the new aspect is system being asymptotically order zero. And this we phrase in a similar way. Again, we take some index x and y in fk, the tolerance, and then we take some index bigger than k. And now we need another delta because we don't want to look at the product. We want to look at whether x and y are give rise to almost orthogonal maps, almost orthogonal elements. And then we want that whenever we have two yet bigger indices, m and n, then if x and y, they're not necessarily orthogonal, but they might have almost orthogonal image at this later stage. And then this almost orthogonality is picked up by the connecting maps from Theorem. Okay, that's what it says. And it's really the order zero analog of this here, of this condition. Okay, why would we even care? Why do we want to make a slightly technical definition more general and maybe even more technical? So here's first theorem using the ideas of Beckett and Kirchberg and this characterization of the approximations given by Brown, Carrion, and White. Goes as follows. Let's start with the separable unital and nuclear C-star algebra. And then there exists a system of completely positive approximations such that when we take the lower row, the associated lower row, which consists only of the finite dimensional C-star algebras, such that this has the following properties, namely it is asymptotically order zero in the sense I defined, and such that the induced map comes from the maps from A to the finite dimensional C-star algebras. Okay, for each finite dimensional C-star algebra, we have a map from A to the finite dimensional one, and then we can look at X, and this is just the inductive limit inside F infinity. F infinity is the sequence algebra. Okay, and then A maps canonically to this F infinity, and the image is this capital X, and this is an inductive limit. And this map is then an orthogonality preserving complete order isomorphism. Okay, and so X you can think of as sitting in F infinity as an operator system, not operator system in the sense that it contains the unit of F infinity, but it contains an element which is just the image of the unit of A, but which is not exactly the unit of F infinity. It's just a positive element, which is a matrix order unit. So it's an order unit of this operator system. Okay, and orthogonality preserving means if you have orthogonal elements in A, then they map to orthogonal elements in X. And orthogonal, by orthogonal, I mean the product of an element with another element, and the multiplication is that of F infinity. And you can think of this X as something, it's the image of A under an order zero map, so it's a bit like a cone over X inside. So we realize something which is a bit like a cone over A, sorry. Something that's like a cone over A inside this algebra F infinity. Okay, and again, if A and all its traces are quasi-diagonal, then one can arrange that the system is asymptotically multiplicative. And also that in that case, psi is an injective star homomorphism And moreover, in this case, if we have a lot of traces, then we can also arrange that for the connecting maps from fk to fk plus 1, we have induced maps in the opposite direction between the trace spaces. So t small 1, t small 1 are tracial functionals of norm at most 1. So the tracial cones. And the maps from rho k to rho k plus 1, from fk to fk plus 1, they induce maps in the opposite direction. And that's because these rho k, they consist of order 0 components. That's what we can arrange. And these maps back, they're simplicial maps, they're affine maps between the tracial simplices, such that when you take the inverse limit along the system, on these simplices, then you recover the trace space of A, or the tracials of norm also. Okay. So whenever we have a nuclear C-star algebra, then we do find these systems of finite dimensional approximations, such that A can be described by X in this form. Before I say a bit more about what X looks like and how to recover A, I want to flag up the question whether this characterizes nuclear C-star algebras, whether we can recover nuclearity in particular. And the answer is yes, and that's very good, but it's a hard answer. So here's a theorem which was spelled out by Sato and appears implicitly in work of Ozawa. And it's a one-sided version of the completely positive approximation property. Goes as follows: the separable C-star algebra A is nuclear. I mean, separable is just a red herring. This is it's not so important. Is nuclear if and only if the following holds: there are CPC maps phi k from finite dimensional C-star algebras fk into A, such that when you take the induced map capital phi from f infinity to a infinity, now f infinity is just product over f over sum over f. It's of the fk. It's a sequence algebra, and same for A. It's a sequence algebra. So if we have all these maps phi k, then they induce a map from f infinity to a infinity, such that the unit ball of A is contained in the unit ball in the image of the unit ball of f infinity. Okay, and this is a hard theorem. So the forward implication is not so hard, follows directly from the completely positive approximation property, but the reverse implication is hard, because to arrive at the completely positive approximation property, one has to recover the maps psi k, and these cannot be recovered easily from the maps phi k. At least this doesn't seem possible. And instead, the proof that Ozawa, respectively Sato, give is that they show that the bidual of A is injective, and then use Alain's work to conclude that it's hyperfinite. In fact, I think one would get away with just concluding that it's semi-discrete, but this one has to do. And then, as a corollary from this, we get that in the situation of our theorem, situation before, where we had this system of, this inductive system of finite dimensional C-star algebras, and we have the map psi, which is a complete order isomorphism between some C-star algebra A and this inductive limit X, then A is nuclear, because it fits exactly with this theorem. Okay. There's an a slightly alternative approach by doing the following. If we have this system and we have this isomorphism, then one can observe, and it's not very hard to observe this, that X or A are isomorphic to subquotient of a UHF algebra, of the K algebra, for example. And this is just as in Kirchberg's subquotient theorem, but the technical part of that theorem is we can skip this because this is already subsumed in the fact that in our system things are set up in a way that these errors are summable. Okay, and this is what makes Kirchberg's proof a bit hard to read, and this is already built into our system. So we can also exhibit A as a subquotient of the UHF algebra, and also, so it's a quotient of a subalgebra of the UHF algebra, and the subalgebra is also image of a conditional expectation, as in Kirchberg's subquotient theorem. And this characterizes nuclearity. But again, for this we need semi-discreteness of the bidual of M to infinity to arrive at the completely positive approximation property. So this approach is not easier, but it's a little different. I think it's worth pointing this out. All right, so now what do we have at this point? In particular, we have that when A is a separable universal nuclear and say sufficiently quasi-diagonal C-star algebra, then we know how to recover the trace space, the traces from a suitable system of completely positive approximations. And we also know how to recover the multiplicative structure via the map psi from A to X, because this is this is completely autoisomorphic, and and this also means that in terms of X, and therefore in terms of the system, we can describe projections and unitaries and partial isometries, because projection, it's a self-adjoint idempotent, and being an idempotent, describing that, characterizing that, involves the multiplicative structure, of course. But since in the quasi-diagonal situation we can describe the multiplicative structure in terms of the system, we're good. And this means that since our constructions is also all compatible with matrix amplifications, we can describe K-theory in this setup. That works fine if we have enough quasi-diagonality. However, if not everything is quasi-diagonal, then we can still describe traces in the same way that I said earlier, as an inverse limit of these tracial simplices of the finite dimensional C-star algebras. But we can even describe K-theory. And the crucial observation is this: if P is a projection, then it's a projection in A. Then we have the map psi from A to X, and for this map psi, we have the following identity. I assume A is universal to avoid technicality. Psi of P squared, and this squared here is now the multiplication inside F infinity. So it comes from the multiplication in the finite dimensional C-star algebras. This here is the same as psi of P times psi of the unit. Okay, so we use multiplication in the finite dimensional C-star algebras, and this throws us out of our system, throws us out of X, but not too far. So we have this identity here, and this describes being idempotent inside this inductive system X. Okay, and this is for projections, but similar. We have something similar, something very analogous also for unitaries and for partial isometries. And this way, one can always describe K-theory for nuclear C-stars in terms of their approximating systems. And I don't spell out the details now, of course, but in principle, this works. And then this means that we can analyze nuclear C-star attributes in terms of asymptotically order 0 inductive systems of finite dimensional C-star attributes. We can compute K-theory, describe cases, describe traces, and so on. That's all fine if we already start with the C-star algebra, but I haven't really said yet whether I can read off from a system. If you just give me the system, whether how can I determine whether this belongs to a C-star algebra or whether it's just some funny system. So we want such a characterization, and we want an intrinsic characterization. I want to be able to only look at the system, or at the inductive limit of the system at X, and see whether this limit X can be equipped with the C-star structure. An abstract setup is very easy to pick up. Let's look at the operator system X, comma E, and E is a matrix order unit. It's not the unit of F infinity. It's just a positive contraction inside F infinity. But which has the properties of a matrix order unit for X, not for F infinity, of course. This is completely order isomorphic to a unital C-star algebra if and only if three conditions hold. First, E commutes with X, and commuting involves the product of F infinity of the C-star algebra which contains X. So E commutes with X, and we want this property that that when we take X squared, so the set of all elements X times Y, where our multiplication is in F infinity, this is the same as X times E. Okay, so this means whenever we have two elements, little x and little y, then X times Y is the same as Z times E for some element Z in X. Okay, and this is something that happens in the system, in the systems we come up with when we start with nuclear C-star algebra, and we can make this an abstract condition on the system. And we also want a non-degeneracy condition, which is fairly easy to guess. So if X times E is 0, then X has to be 0. Okay, for all X. Okay, and this way we can describe very easily multiplication, because we have this here, this condition, together with the commutativity condition. This allows us, if we have little x and little y in X, then there's some Z, such that X times Y equals Z times E, and Z is then simply the product of X and Y in the C-star algebra A, which we construct in this way. Okay, and one needs this non-degeneracy condition to make the product unique. All right. What are the next tasks from here? Of course, one thing one really would like to do is describe KK theory in terms of systems of CP approximations. and then ideally, I would love to be able to prove coordinate formulas in terms of systems of CP approximations. And what lurks behind this is, of course, the hope to say something about the UCT. And on the side, I would quite like to see a C-star algebraic proof of the fact that nuclearity passes to quotients, but it feels like we're quite far off from this. We've tried pretty hard, but there doesn't seem to be a shortcut. Okay, and that's what I wanted to say for today. Thank you very much.
All right, thank you very much, Wilhelm, for such a nice talk. If there are questions or comments, just please go ahead and ask Wilhelm.
Yes. I have one comment. When you were saying that you want to find the KK theory in these terms, I think it would be much easier to find the E theory, namely the theory of asymptotic morphisms.
Yes,
because that's where
sure.
you are. I mean, that's where you are. You are exactly in that framework. So
yes,
and especially
yes, I completely agree.
Yeah, okay. So I think that should make things very easy. The other thing which I wanted to comment about was the fact that in a way, there is a problem which might not be very difficult and which is behind the scene, because you are taking finite dimensional C-star algebras, but then the morphisms that you are considering are completely positive maps and so on. So it seems like you are concentrating on special objects among operator systems, or complete, and that somehow there is behind the scene the need for a characterization of which are the operator systems which intrinsically come from a C-star algebra, which yes. you are essentially using when you take this order unit, but I think that somehow one would gain if one had because then it would allow also to approximate nuclear C-star algebra, not necessarily by taking finite dimensional C-star algebra, but by taking operator systems which get closer and closer to C-star algebra somehow. You see what I have in mind?
Yes. So for this abstract characterization, it's not important that the F lambda are finite dimensional. That's not important for
good.
These things to work, of course.
Sure.
And somehow these convex combinations of order zero maps. I mean, order zero maps. They want to be extreme points in a certain sense, like star homomorphisms are extreme points.
Yes.
And
exactly.
And,
you see,
and so,
what I had in mind
so
was,
the
yeah.
So the end result, the limit x is also it's something like a convex combination of extreme points, but they are not really extreme points in norm, and we haven't grasped really in which sense we can describe this as extreme points of a convex setup.
You see, that's exactly what I had in mind, because what I was thinking is that well, in simple situations, you have the extreme points of the 0-1 interval, which are idempotents. And then, I mean, this means that somehow from the convex structure, we can extract already something which is beginning to look like K-theory and all that. So I think, there is a good way, I mean, one should dig more and more in that direction of, extending the notions to operator systems and so on, so that the category is more unique, I mean, more unified. It's not just that you have C-star algebra and morphisms which are rather special, but you have the whole thing. The objects also should be more general. But this is what you were saying when you were talking about the fact that you have an operator system at the end of the day. I mean, so
yes. So in principle, in this way, one can, of course, also define K-theory for operator systems in this sense, but we don't have enough examples to really test our hypotheses.
But I think it's very valuable to do that. I think it's extremely important to do that, because for the reason that, when you want to approximate, for instance, physics by finite dimensional stuff, I mean, you don't expect to have finite dimensional C-star algebras. You expect operator systems. And then you want to have things which replace K-theory. So digging in that direction is extremely relevant, I think. Yes.
We'll keep digging.
Yeah.
Thanks.
Can I ask a question?
Wilhelm, hi.
Sure. Yeah.
I would like to know this limit space X. It depends somehow of the choice of your original approximation with the phi lambdas and psi lambdas. So if you change this, how much does it depend on this original going down and going up maps?
I mean, if it's in the end, it doesn't depend anymore because it's isomorphic to the same C-star algebra. But of course, to arrive there, we had to pass to subsystems all the time to make the errors summable. And then if you start with just a system at the beginning, then it won't give us anything. But if you pass to subsystems to make errors summable, then you make the system thinner and thinner, and then it doesn't depend anymore eventually. But this one has to do in any event, I mean, passing to subsystems and eliminating these errors. That's
okay. Thanks.
Well, I have a question.
Yeah.
I have a similar question concerning uniqueness. So from a C-star algebra A, you constructed this space X, which is of course unique up to a complete order isomorphism. But conversely, if you have the X, what can you say about all the possible C-star algebras that it could come from?
I mean, if it satisfies these properties here, then there's only one C-star algebra. Then the C-star algebra is completely determined. But yeah.
Could I?
But in order to get the
Chris?
K-theory, you need not only the X, but you also need the image of 1 and so on. So it could not.
Yeah. I mean, E is.
It could not be completely
image,
unique. I mean, even for the K-theory, you need some additional information.
But E is the image of the unit. That's.
Yeah. So you need the X and the image of the unit. But
So can I draw a bit of an analogy here? Because you can think of X as an abstract operator system. And when you think of X as an abstract operator system and E as the order unit, then the C-star algebra associated with this is actually going to end up being this enveloping this minimal C-star algebra. And so the sense in which you have to have X and E is also canonical. It determines the C-star algebra in the same way.
Yeah, uniquely. Yeah, sure.
Mm-hmm.
So it's a unital operator system, what you have, yes.
yeah. Okay, but are you saying that when you start with the C-star algebra, I mean, you're saying that you could not start with two different C-star algebras and arrive at the same X?
No, not in this way. No. X determines the C-star algebra uniquely.
Saying, Christine is saying the right thing, namely it's a unital operator system and it has a canonical enveloping C-star algebra. There it's equal to the enveloping C-star algebra. So that's it.
So the X is really completely equivalent to the A.
Yes. And the task of this was to find conditions on X so that I can read off from X alone without mentioning the C-star algebra whether there is a C-star algebra, whether X is isomorphic to a C-star algebra, and conditions which can be read off already at the level of the inductive system. That was one of the tasks. But then, of course, and then, as one would expect, that it is possible to read off K-theory from the inductive system, but it can be read off really already at the level of the system without having to know the whole C-star.
Okay, I see. Thank you.
In fact, it connects with my question because I mean, what would like to have would be good conditions on a unital operator system so that it's equal to its enveloping C-star algebra. And would like
Yes.
to have simple conditions that actually characterize this.
Yes. And the notion of Blackett and Kirchberg of these generalized inductive systems with these asymptotically multiplicative maps, this already went in this direction, but there was a drawback at the time because this only applies to quasi-diagonal C-star algebras, only when it's a very special class of C-star algebras, which is, by the way, not closed under taking quotients. Quasi-diagonality does not pass to quotients, and then it's maybe not so worthwhile describing K-theory even at the level of the systems, because you don't have short exact sequences at hand. But in this setup, with these asymptotically order zero maps, this does pass to quotients. It's completely general. So we do have short exact sequences, but we haven't worked out yet how to read these off from the systems. This we still have to do. But this must be possible because this, I mean, the notion works not only in the quasi-diagonal case, but in complete generality for nuclear C-star algebras. But again, passing to quotients is the crux. It's yeah. Oh, there's something in the chat. Where do I see the chat?
So are there other comments or questions? Well, in that case, we thank Wilhelm again. Next week's talk is by Shinichi Ogani, if I pronounce it correctly. So thank you very much, everyone, for coming, and see you next week. Thank you very much, Wilhelm.
Thank you for coming. Thanks. Bye-bye.
Thank you. Just Wilhelm, would you be happy we upload the video online?
Sure.
Okay,
sure.
perfect.
Do that.
Wonderful.